Hello everyone, let's begin today's session with an important concept in algorithm analysis, that is asymptotic notation. This helps us understand how algorithm behaves when the input size grows very large. The first question is what is asymptotic notation is. Asymptotic notation is used to express the upper and lower bound on the performance of an algorithm. The focus is on how the algorithm behave as the input size n became very large. There are three main notations. The first one is big O notation. It represents the upper bound, or we can say worst time case. Then second one is omega. It represents the lower bound, or we can say best case. And the third one is theta. It represents a tight bound, meaning both upper and lower limit are the same. Now let's understand some important properties of asymptotic notation in a simple way. Key properties are, the first one is constant multiplication. Doesn't matter if you multiply your function by a constant like 2 or 10. It doesn't change the overall time complexity. For example, whether an algorithm takes n steps or 10n steps, we still consider is order of n. The second property is transitive property, or we can call it chain rule. If one function is slower than another and that second one is slower than a third one, then the first one is definitely slower than the third one. It's just like if A is slower than B and B is slower than C, then A is also slower than C. And the third property is reflexive one, or we can call it self-bound. Every function is obviously bounded by itself. So saying a function is order of fn is just like saying a person is equal to themselves. It's always true. The fourth property is symmetric properties. It's only for theta. If two functions grow at the same rate from both sides, we say they are tightly bound. So if f is theta of g, then g is also theta of f. It's like saying we are strongly competitors. The last property is transpose symmetric, or we can call it reverse view. If one function is an upper bound of another big O, then the other one is a lower bound of the first omega. So if f at most as fast as g, then g is at least as fast as f, just looking at it from the opposite side. You might wonder, why do we focus so much on large input sizes? Because in real world problems, input can be used, so we need to know how the algorithm behave as n becomes n large. We approximate function of n using simpler expression like n log n, etc. Real-time performance may vary due to hardware, but asymptotic analysis give us the long-term trend. When you are trying to calculate time complexity, here are some quick rules. A single loop gives us order of n complexity. A nested loop usually means order of n square. Consecutive statements just add their complexities. If else branches, take the worst case. Having the input each time, that's typically order of log n. Classic example, binary search, order of log n. Now let's talk about the master theorem. A tool is used to solve divide and conquer recurrence relation. It's used for recurrence like t of n is equal to a dot function of t n by b plus theta n to the power k dot log p n, where a is the number of sub problems, b is the division factor, k is the exponent of n, and p is the exponent of the logarithmic term. This slide lists the different cases of the master theorem based on the comparison between a and b to the power k and the value of p. These cases helps us directly find the time complexity without solving the recurrence from scratch. Let's look at an example. A function of Tn is equal to 4t n by 2 plus n square. We compare it with the format we have learned in previous lecture. A is equal to 4, b equals to 2 and k equal to 2. Here a equal to b to the power k. So it's the case 2 with p equal to 0. So the answer is time complexity of n equal to theta of n squared dot log n. One more example, a function of Tn is equal to 3t n by 4 plus n. We have a equal to 3, b equal to 4 and function equal to n. So k equal to 1, p equal to 0, b to the power k equal to 4 to the power 1, that is 4, and since a equal to 3 which is less than 4. This falls under case 3, which means the final result equal to theta of n. Finally, let's talk about the guess and confirm method. This is especially useful when the master theorem doesn't apply. Here's how it works. First, you guess the time complexity based on how the recurrence looks. Then, you confirm that guess using mathematical induction. For example, take this recurrence. A function of t is equal to root n dot t root n plus n. This doesn't match any of the master theorem case. So we try a guess dash too big, theta of n log n. Try a guess that too small, theta of n. Eventually we find that the right answer is theta of n log n. So this method is all about making smart guesses, then proving them. And with that, we wrap up asymptotic notation. We now covered big O notation, omega, and theta notation, their properties, time complexity estimation techniques, master theorem and its examples, and finally the guess and confirm method. These tools will help us analyze how algorithms scale. In the next lecture, we will begin a new topic, amortized analysis, which helps us in understanding the average cost of operation over times, even when some operations are occasionally expensive. Thank you for your attention.